Okay, just to recall what we have discussed. So this search method we have discussed. So these are one dimensional. Okay, these are actually linear search, I mean line search techniques, one dimensional search methods. Okay. Also we had dichotomous search, then these are actually known as linear line search methods, because the search point that we have been searching was only on a line. That interval we had been reducing. After that, the final interval we have found. So there was a line search. So for multivariable search, we have seen for that was a univariate search, where we have gone vertical, horizontal or vertical, and then horizontal and vertical, and we'll repeat the process until we reach the optimal point. So that was for univariate method. For univariate method, we keep other direction as fixed, and then only one direction is changed at a time. N minus 1 variables are fixed. So now, but remember here we do not use gradient method. We do not use. We only use the for finding the lambda star, the step length. We have used the derivatives. Otherwise, this method is actually derivative free method. In order to optimal, that was the optimal length, optimal step length, that how much we should make the movement. Okay. So that was for, just to recall, the univariate method. And then if we have this kind of problems, so try to solve them using univariate method, starting from the given points are here. So here it is 4 variables are there. So that is why. So this x equals for this case x is a variable x1, x2, x3, and x4 in this case. Okay. Or we can write in this form, that is this function. Now, since univariate method, it has a, it's a very simple method and easy to implement, but the convergence rate is very slow. It has a linear convergence. It will sometimes it will not be able to converge actually. It will oscillate during the final interval of uncertainty. And then this we will use the concept of gradient. Just to recall, the gradient, it's a very important property. And then if we try to go up, so that is there are two words actually step. This means either we rise sharply or we fall sharply. Okay, almost perpendicular in this direction, almost perpendicular direction. So either we go up or we go down. So that is the step. So that is why in machine learning also, in other optimization techniques also, so these are very important. Steepest descent method, steepest descent or ascent method. Normally we do not discuss this ascent method, because finding the maximum is actually equivalent to finding the minimum of the negative function. Okay. So this can be just if you just reverse it, flip it vertically, So this will be actually, if you flip it vertically, so then you will get the valley. Earlier it was a, mountain, it was a peak, now it has become a valley. So that is why one is sufficient. If we go that steepest descent method, then it is sufficient. So yeah, and this is the contours that we derive. So these the contours are on the surface. So if we view in the two-dimensional space, it will look like this form. So if you go down or go up, depending on the situation, so it will look like, so this is ascent method, so it will start from the beginning. Okay, it will go up. But if it is descent method, so it will go in this direction, so descent method. So that's the idea of gradient based method. Gradient steepest descent. So we'll discuss the steepest descent method. Which is also known as Cauchy's method. So the thing is, in this case, we need to calculate 3 steps. So for step 1, we calculate, you remember what is the gradient of a vector? Gradient of a function at some point. So this was the perpendicular direction over the tangent plane. So if we plot a tangent plane here, so this would be the perpendicular. So what we do here, we take the negative direction. That means we are trying to get this direction because we want to go down. Okay. So with this help, let us try to calculate the lambda value. So how much we can, either we go this much or we go this much. So what will be the lambda value? So that we have to find out how much we can step. Now, if we have this xi is this is point, the next point will be xi plus 1. So next iteration will be xi plus 1. Okay. And these are actually in n-dimensional space. For n equals to 2, if you think n equals to 2, then it is easy to visualize. And we remember that at the point, if it is optimal, then the necessary condition, first order necessary condition satisfies. The gradient will be 0. This 0 means actually 0 vector, depending on the dimension of the function. Okay. So if it is not 0, at least we will try to make almost 0. For example, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 2, or something like this, depending on the tolerance that will be given. How much approximate value we can allow. So that is the idea of steepest descent method. Now what is H? H is the Hessian matrix. Okay.
Sir?
Just tell me.
Sir, in the third step, isn't it xi plus 1, sir?
Yes, xi plus 1.
No, sir, to check gradient of f of e, it's given as xi. Should it be xi plus 1?
No. For every step, okay, you are telling about this, right?
Yes, sir. In the second step, we have updated the point of consideration.
Okay. Yes. This should be yeah, I plus 1. For I equals to 0 at the starting point, we'll take I equals to 0, 1. Okay, if we start with x1 and so on. Okay, you understood that, right?
Right, sir.
So yeah, so our aim is to make check whether this is 0 or not. That would be tolerance. Sorry, tolerance will be given. So if you try to find out the solution for this problem analytical way, you start with 0 0. That is not a problem if we here. So first we'll take the first order partial derivative with respect to x1 and x2. Okay, then this will be so 4x1 plus 2x2 plus 1, and with respect to second variable, so this will be 2x2 plus 2x1 plus plus this would be minus 1. Okay, now if we try to make it 0 0, because we want to find out the minimum point of the function, so for that if we make it 0, so this will be give you a system of linear equation. Okay, and for that if you use the Gauss-Jordan method, then we can find that this is the exact solution. This is analytical solution. The exact solution is this one, exact point, exact minimum point. Okay, and we can substitute these values. So you can calculate minus 1, 2 into minus 1 whole square plus 2 into minus 1 into 1.5, then plus 1.5 whole square, and this would be minus 1, then minus of 1.5. So you try to calculate whatever the value will be, you put it there. So that would be exact minimum value, and this is exact minimum point. Now we want to implement the idea. So if we remember this same problem we have solved, the minimum value will be this 1 point minus 1.25. But if we use the univariate method, we have seen that after 2 iteration we have reached to up to this. But then we have to go for the next iterations. Okay, until we reach the near to the point, minimum point. So as we have mentioned earlier also that this is a very slow method, so we need a faster method. So that is steepest descent method is a very fast method. Note that these are actually we are solving unconstrained problems, but in multivariable case. So since this is given, so the first task is to calculate the direction. So which direction we should follow? Either we go this direction or go this direction. I remember also in the univariate method we have gone either horizontal or vertical direction. But now we can move along angular direction also. We don't have to go by vertical direction because we want a faster method. So we need to use the slope of the curve or the slope of the what do we call it? Yeah, descent of the, there is a steep of the surface. So for that we will try to find out. So suppose you are here, you want to follow the target. So that is our target point. So you start with x1. So okay, you start with x1, and then lambda amount of jump or lambda step we move. Step length is lambda 1. So we move in the s1 direction. So s1 will be actually calculated by the gradient, negative of the gradient. Okay, so we reach here. We try to verify the optimality here. If it is not optimal, we find lambda 2 in the S2 direction. Similarly, we repeat the process up to we reach the SN point and the target final point. Okay. For example, if you try to calculate the step length, so this would be our step length. Lambda 1 will be okay, x2 minus x1 by s1. S1 is a, remember, this is a vector, x1, x2, and so on. It would be like this form. So these 2 points. So this is the point. So if you think about this two-dimensional case, so you can visualize it. Okay. Now let us understand the step 2. So how to do that? So the step length is select the step length in that direction to reduce fx. We want to reduce the fx function. So that is why we need to find the next step xi plus 1. Remember, this is suffix, not I plus 1. So xi plus lambda into si, or we can write lambda I equal to. We try to find the lambda direction. Lambda is the value. Okay. So this is the method actually. So this is a strategy. So general strategy for gradient method. All gradient method will have the same strategy. This is a strategy for all gradient method. And then let us find the strategy for steepest descent method. So this steepest descent method, search direction, we will always fix as the fi. Fi means evaluated at minus f of xi actually. Okay. So this is evaluated at the xi point. Okay. So for step 1, we have defined this one. So for step 2, we will try to find out the optimal step length. So how much we will move, how much will go down. So that is decided by this one. And then after reaching from xi to xi plus 1, we have to evaluate whether this point is optimal or not. We have to check. So first order necessary conditions. So that here we will check that delta xi plus 1 is 0 or not. So if it is 0, then we have reached our minimum point. Okay. So that is the idea. So how to pick this lambda, that step length, how to pick it? So there is analytical method is there, another method is there. So numerical method. You can use the bisection method because you know these 2 points. So you can measure the distance. So approximate distance you can get by this bisection method, and then Newton-Raphson method and other methods. But then again, this will give you the approximate solution. But if you want to get the exact solution, you have to go through the analytical method. So for this analytical method is actually uses the Taylor series formula. So Taylor series formula, it will give us the Hessian matrix. It uses the Hessian matrix. If you remember f of xi, that second order Taylor series formula, f of x plus h equals to f of x plus h into f dash of x plus second order this. So this was for single variable case. But for multivariable case, we have seen that this would be the Hessian matrix. We will take the help of Hessian matrix and the gradient. Okay. So now with this Taylor series formula, what we will do, we will try to differentiate with respect to lambda, because we want to find the lambda value. Okay. So what we denote this delta xi equals to lambda into si. We substitute if we want to try to find out. For example, this lambda into si. This is lambda into si. So this is lambda into si. And then, okay. So for this, if we differentiate this function, differentiate with respect to lambda, then we will get this function. And because we want to find the lambda value, so we will make it 0. So once we make it 0, then the function will be simplified, the expression will be simplified, and finally what we will get is this one. So S transpose into Si divided by Si transpose into Hessian matrix into Si. So this will give us the minimum of the approximating function. This will help us to reach the from xi to xi plus 1. So how much this lambda that we can go down. Okay. Because we have that assumption is this one si. Si direction is the negative of the response. So here it will be this lambda value we calculate. So once it is calculated, then we can go to step 3. For step 3, what we do? Okay. Now the reason why we use this one, okay. The same thing. We have to satisfy the first order necessary condition for single variable. Now we are talking about for multivariable case. Okay. So there is so this is actually how to find the lambda value. Yeah. After finding this lambda value, we can go for this one. We can calculate the xi plus 1, and then we verify them whether it is optimal. If it is not optimal, we repeat the process. It will be repeat the process in iterative way. So if we just try to calculate for hand calculation, the function is this one, x1 minus x2 plus 2x1, the same function we take, and then 2x1 into x2 plus x2 square, and the initial starting point is x1 equals to 0, 0. So first task is to find out the gradient. So gradient is actually found in this way. Now you have to evaluate f of x1. So that means in place of x1 we will put 0, and in place of x2 we will put 0. So here also 0 and again 0. So we'll get this one. Okay. Now in order to find out the Hessian matrix, what we have to find? The second order partial derivatives. For the second order partial derivatives, it is actually a constant, it becomes constant. But if you think that sometimes a cube is there, then some x term will be coming here or there. Okay. But this is a quadratic function. So here we are directly getting a constant matrix. In some problems, there can be x1 can be there, or x2 could be there also. Let us not discuss that now. We'll. So for this particular problem, we have this Hessian matrix. Now we have to calculate the first iteration. So S1, let us start at x0. So S1 will be the negative of this value. Okay. What we have calculated? Our gradient was gradient of 0, 0 is this one. So if you multiply with -1, so this will be the first component will be negative, the second component will be positive. So that is why our S1 direction is this one. So -1 and +1. Then we have to find out the λ1 value, the first step length. So this is given by this formula. So S1 star, S1 transpose into S1 divided by S1 transpose into Hessian matrix into S1. So for that, why we need the transpose? Because we have to do the matrix multiplication and the dimension should be consistent. Otherwise, we cannot do. Okay. So this is -1, +1, and then -1 and +1. So we multiply it, matrix multiplication done. We do the matrix multiplication in the denominator also, and we finally note that λ1 is equals to 1. So this value is 1. So hence, let us define the new point x2. x2 is x1 plus λ1 into s1. So s1 we have this value. So let us substitute s1 here, and then we try to find out the x2 value. Now the next task will be f of x2, whether it is 0, 0, because we have two variables, whether it is 0, 0 or not, let us check. Okay. So now we can see here, after substituting these values, x2 is now -1, 1. Okay. -1, 1, this value is there. So if we substitute these values, we can get -1 and -1. So this is not equals to 0. So this is not optimum point. So we move to the next iteration. Always we remember that at the optimum point, this would be 0. The gradient function will be 0 because this is a first order necessary condition. Okay. Then we move to the next iteration, that is iteration 2. So for iteration 2, we'll start with x2 and we'll try to find out the s2 direction. So which direction we have to move? Okay. And this one is nothing but the negative of the previous. Every time we need to evaluate this one because this value will be applied. I mean, it will be useful for the next iteration. So this -1, 1 into -1. So this is now 1, 1. Similarly, we calculate the λ2 value. Now the λ2 step length is now 1/5. We do this calculation and we get this 1/5. So hence the new point, okay, x3, we define x3 as a x2 plus λ2 into s2. So this will become now λ2 is multiplied by 1, 1. So this is nothing but we have -0.8, 2. Okay. So the task is to evaluate f of x3. Gradient of f of x3. So we have 0.2 and -0.2. This is again not 0, so not optimum. So I move to the next iteration. And at x3, we'll start at s3 will be the next direction. and this is calculated in this way. So this is, try to complete this hand calculation, complete these iterations, okay, and verify that for iteration 3 we will get this such, for iteration 4 we will get this much. This is actually very close to 0 0, and if you go for iteration 5 or iteration 6, the lambda will be 0, and ultimately the analytical solution, that was our original solution, analytical solution, if you use the linear algebra concept by Gauss-Jordan method, we have seen x star is, that x star is actually -1 comma 1.5. So here it is also actually matching. Okay. Now we will actually see a MATLAB simulation also, that how do we reach to the point. Okay. But it is actually MATLAB, it will take some, my computer may get slow. So that is why I will show that simulation at the end. Okay. Now there is another method which is called yeah, so this is actually known as conjugate gradient method. So if you remember the conjugate direction, okay, let me just recall. So this is our direction that we have. The direction S1 is conjugate to S2 over the Hessian matrix H is given, the conjugate direction S1, it will be given in this direction. That means it will take always the perpendicular direction. And for conjugate direction, we need to define a Hessian matrix. So based on this Hessian matrix, we can remember. Okay. For example, this is S1 is this much, 1 minus 1 comma 1, and S2 is this one. Then, and the Hessian matrix is supposed for this particular example, we will have this much for 2 and 2 2. Then if we multiply this, then these are actually 0. But if Hessian matrix, suppose for some example, if we have this one, Hessian matrix is an identity matrix, then S1 and S2, these two directions are actually S2, S1 and S2 directions are perpendicular directions, are orthogonal to each other. That is in the usual sense. So this some comments on this conjugate method. It is actually, so for steepest descent method, we have seen that uh, compared to univariate method, steepest descent method is faster. But steepest descent method, steepest descent direction is not fast enough. This is also slow. It needs many iterations. So we need, definitely we need a, I mean, there is a need, we need a better method which can give the final solution in less number of iterations. Okay. So this, let us keep the steepest descent method. The idea of the structure is kept, but we want to improve by the conjugate direction. For steepest descent method, we have seen the direction was actually negative of delta f of xi direction we have taken. Okay, this direction we have been applied. But now we will apply the conjugate direction of this method. So if we apply the conjugate direction, it will subsequently improve the quality of the search. Maybe within 2 iteration, it can give the solution. Earlier we have seen after 6 iteration, we are getting the exact solution. But this will help us to get within 2 iterations. Okay. So because the property says for any minimization method, the conjugate direction has the quadratically convergent. That means the convergence rate is quadratic 2. Rate of convergence is 2 here. So if you don't know the convergence rate, just search on the Google. So those who have studied numerical methods, I think they know this, the convergence rate, rate of convergence, of order of convergence. Okay. Okay. I would say read or recall. Okay. Now the benefit of this conjugate direction is actually if the number of variable is n, then it will take exactly n iterations to reach the optimal point. So here we have only x1 and x2, 2 variable. So this method will converge within 2 iterations. So it was supposed to converge within, if it is supposed to give you the optimal solution within 2 iterations. So for the same or different problem, for example, if we take, for this problem, so only 2 variable, so it will n equals to 2, so it is supposed to take 2 iterations. But if we have a 3 variable case, so the method will take only 3 iterations to give the optimal solution. But remember, this method is applicable for the functions of a quadratic function type. So that is one. It cannot be applied to any function. For example, if we have this cube or to the power 4, we cannot apply this method should not be applicable. Okay, these results are not valid then. So for this purpose, so this is a special case that it can solve these problems very quickly for a class of problem. The class of the problem is actually quadratic function type. And this is the standard form of a quadratic function. Okay. So let us understand the algorithm. This conjugate gradient method. It is also known as Fletcher-Gibbs method. Then the first aim is to minimize the function effects. Calculate the gradient and the Hessian matrix from the given function. Set the initial starting point. Then start with arbitrary x1 and iterate the number from I equals to 1. So the step length that we have calculated, step 1, we need to find the direction where beta is actually will be the conjugate direction. Okay, now in steepest descent method we have only this much, but now we are actually adding some more. So we are actually changing the direction of our search. So this beta, with the help of this lambda I and this much, and si minus 1. So I equals to 1. So we'll have s1 will be minus delta f of 1 plus beta 1 into s0. So let us see one. Let us see the for the step 2. Okay. So this lambda I, the step length, now we will have this much. This lambda y transpose into, earlier we had S transpose, Si transpose S, because we had used the direction Si. Now we have changed it. Okay. So after finding this lambda I, again we try to find the xi plus 1, and then we evaluate xi plus 1, whether it is 0 or not. If it is 0, then we have reached the optimal. So let us take the same example. So decision variable is number of n equals to 2. So we are supposed to get the minimum point at most 2 iterations. Let us verify whether we get. So we calculate the first order partial derivatives, second order partial derivatives, and try to find out the gradient. Okay. And we evaluate the starting point as x1 equals to 0, 0. And also find out the Hessian matrix of this form. Okay. So for iteration 1, what we need to do, this one, as this the gradient of this one, and S1 detection is this one. And so if you remember that S1 direction will be minus Sy plus gradient of F divided by, so it is a starting point. Okay, we are starting with a 1, so there is no 0. So this is, I mean, the first S1 will be the same direction whatever we have seen in the gradient descent method. It will be the same as before, just a negative, because we are starting with I equals to 1, and we have the quantity here is I minus 1. So beta I minus 1, so this is not actually valid. So only we need this much. So this is not true. So if we find this direction, okay, let us apply this direction only. And here, in place of this S1, we will substitute these values and calculate the same length that we have found in the gradient descent method also. Okay. Now the change will come here at iteration 2. Okay, all these values will be same, not optimal. Okay, then at x2 we have found this gradient of f2 is minus 1 comma 1. Okay, now this vector we try to find out the length, that is the absolute value. So we have to find out the square. So minus 1 square into plus minus 1 square, and we divide it by delta f1. So delta f1 was in the previous step. Yeah, delta f1 was minus 1 comma 1. So here it is minus 1 whole square plus 1 whole square. So 2 by 2 again it is 1. Okay. So that new direction S2, the S2 direction will be, so minus of this one delta f of 2 into beta. Beta we have calculated here into S1. S1 is there. So after simplification we get 0 comma 2. S2 is the 0 comma 2 direction. Okay. So once we get S2 direction, so we can calculate the lambda 2 by the previous knowledge. So this one was multiplied, and now we can find that lambda 2 is a 1 by 4. After simplification we get this one. Okay. So we find out x3. Okay. x3 is equal to this value, x2 plus lambda 2 into s2. So we find out this. So minus 1 comma 1.5. So that was our actually that original solution we have reached. But if you try to find out f of x3 now, so remember we had 1 plus 2x plus 2x1 plus, so if you remember, yeah, 4x1 plus 2x2. Okay, so this is the for iteration 2. In the iteration 2, step 3. So step 3 is check the optimality at x3. So this is how we get here. So we find out 1.5, 3 by 2, and the optimality is satisfied. So x3, that is minus 1 comma 1.5 is our optimal solution. So within 2 iterations we have reached the optimal point. Now you try to calculate, if you do the hand calculation, try to write at most 3 iterations for gradient descent method. But if you calculate for conjugate gradient method, then you will get the solution within 3 or 4 iterations depending on the number of variables. So these are actually for practice problem. And now let us see it in this MATLAB window. Let us try to find how do we actually implement these ideas. Okay, so this is, I have already actually created. I wanted to explain from the beginning. Before you use this symbolic computing, you need to include the package here. You have to go. I think it is visible. Okay, okay. If I am here, then it is visible. Okay, right. Yeah. So go to add-ons. Yeah. Here we have to go. There are several packages are there. So this is actually symbolic computing. So symbolic math, we need to use the tool package. Yeah. So here you can see I have installed this package. There are many more packages you have to install. These are if your task is to in this field, so you can just take the packages. Simulink is also there. So I have taken this. It is showing installed. Already I am installed. I have installed this package, so I can use now symbolic computation. Okay. So now what we have is here. Let us clear all the thing that we have in the command window. Then let us use the short form, only 4-digit, 4 decimal place. Okay. Then we use the sims. Sims will help us to call them as a symbolic x1 and x2 computation. Then we try to define these functions. For example, if you try to locate these functions, yeah. So if you define this function here, and if you want to run this program, then you will get this function f1. We are calling that function 2x1 x2. Remember the function is 2x1 square plus 2x1 x2 into 2x2 square. Here it is 2x1 square plus 2x1 into x2 plus x1 plus x2 square minus x2. So we have defined this function here. Okay, right. Now if you try to find out f of 1, okay. For example, if this function is not defined, inline function. So if you write f1 of 1, 1, it is giving the same value. But if you try to find out this f of 1, how much it will be? F of 1, 2 plus 2, 4, then plus 1, 5, plus 1, 6, minus 1. So it will be 5. So it is not giving you the functional value. It is just repeating the text. So that is why we need to make it as an inline function, which will convert the this symbolic quantity as a function. Okay, so that is why we need to run again. So now you can find f1 of, so let us the function we are calling now fx of 1, 1. So you can get now 5. Okay, so you can define again a12, 13, so you will get 15 value. So now you can working. It is working now. So the objective function, we have to find the objective function is depending on the x1. So first component is x1 and second component is x2. So we call it in this form. So let us hide them. Okay. Then we have to find the gradient. So for gradient, we need to define. Similarly, we will find the gradient of f. Okay, and then this will give us the only there is a symbolic will be given. So that symbolic function we need to convert into a function value, so that we will get the functional value depending on the situation. Okay. And again, since the gradient is also a function of two variables, we'll call it a gx. So once we find the gradient, our task is to find the Hessian. So again, we find out the Hessian. Let us call this Hessian function. MATLAB is very user friendly, so you can just, you don't have to define program, I mean, explicitly. Inbuilt functions are there, so you can directly call them Hessian. And then again, we can call it a, but for this particular example, we have seen that Hessian matrix is 4, 4, 4, 2 and 2, 2. So if you remember, so this would be, okay, given in this form, 2, 2. So Hessian is reshaped. So let us not write Hessian matrix. So here it is. So Hx, if you call it Hx, Hessian, if you call Hx, so it is giving the actually the function 2, 2. Let me just see here. And then we have to define the initial point. So initial point, let us start with x naught as 0, 0. And maximum iteration, let us give here 10, or we can, since we are talking about the 6, and tolerance, that is how much precision we need. The difference between two numbers should be this less than. So iteration start with 0, and then x is a dimensionless property. X will be our dimensionless. X will call the, so these are the initial points that we have to impose. This is initial task is given. Now the main task is coming here. So the main task is to define how do we actually define this value in this form. Yeah, this one. To calculate lambda I. In order to calculate this lambda I, we have to define this x values. X is a because we have to think about the norm, because for example this value should be, here it is. Yeah, what we want is actually delta f of x0 is should be 0, 0. Okay, but remember this quantity x1 delta f of x1 delta x1, and then delta f of x2 equals to this one. So this should be 0 and 0. But remember, if we take a equals to 3 and a equals to 3, b equals to minus 3, and a plus b again 0. But if we make it a square plus b square equals to 0, then this will imply both of them are 0. b a equals to 0. So that is why we need to take the gradient, sorry, norm for a square value, the distance between the norm. So that is why we need to use the norm, because we are speaking about the two-dimensional, multi-dimensional space. So here it is norm value. Otherwise, if this is a single variable case, then we can find that absolute value. Otherwise, we can have here absolute value. ABS would be the absolute value. And this should be greater than the tolerance. Tolerance we have taken here is this much. And the maximum iteration, that iteration that we are opting should be less than what we have given. So maximum iteration we have taken 6. So less than 6. Within 6 iteration, let us find how much it can get. So for that we have to define the S direction. Si is the negative gradient. So negative of, this is negative of a gradient x, and it is gradient is evaluated at this point x naught. Similarly, we have to define the Hessian matrix. Hessian matrix, and it is evaluated at this point x naught. We have to find the lambda value, this lambda I. For that, what we do now in MATLAB, S, for example, S is a matrix. That S transpose is actually, here it is dash. You put a prime, and because this is a component-wise division, so that is why we will put dot division. The component-wise multiplication will be given in this form: dot star dot division of this one. So these are the functions of actually MATLAB. And then we define the x new. X new is the previous one x0 plus the lambda into s. So this transpose is used because we have to make it, the dimension should be consistent. Otherwise, it will give some error. And then we have to make it that x0 is now, we call it x new. The previous step, we call it x new. So, and we iterate for up to maximum iteration. We'll end the loop. Then, after doing this calculation, we have to find the results also. So for that, we need to use two functions, that is print. So if we use these functions, then we can get the solution here. So optimal solution, x1 is 0.99 and x2 is 1.4. Okay, and if you remember, our original solution is minus 1 comma 1.5. So, so where is it? Before this, yeah, here it is. So this is our original solution, minus 1.5, and by this numerical method, by this approximation, what we can get? Almost 1, 0.992, it is almost 1, and here it is 1.4, that is almost 1.5, and the optimal value 1.24, and the optimal value is 1.25. We have seen the exact solution. Okay. Now, if you want to see the data that we have done in the iteration steps, so here it can be plot it, we can print it in this way. So for first iteration, we start with 0, 0. In the second iteration, we go to minus 1, comma 1. And the third iteration, we will go to this point. After this fourth iteration, we are going to this point. Fifth iteration, and this is a sixth iteration. Okay. Now, if you change the number of iteration here, for example, you give it 10. Then you will see that the exact solution already. Okay. So here is also not, because it is taking only up to 4 digit, so it is not making. Yeah, the left hand side is exact solution 1. It has reached to 1, but the x2 is 1.48. So for that, let us check any other more iteration, or if you take the tolerance as 0, 0, 0, then the same number of iteration, if you do it, then yeah, we are much more closer, 1.49. If you do it here 20 iteration, then what will happen? Yeah. Now you can see that with this tolerance level and number of 20 iteration, we can reach to the optimal solution. Although this, so this is 20, 19, 18, 17, 16, 15, 14. So if you just give, for example, here 15 iteration. Okay. So within, I think 15 iteration, we'll get, so 14 is also enough. So 14 iteration is also okay. So this will give the exact solution. So this is how we can actually implement. So this is theoretical approach. Whatever the theory we discussed, the same code we have developed here. Now I will show you some more results actually, which includes descent. So let us find this function. Yeah, the function is now here it is for a different function. If we have this function, so what will be the minimum value and maximum value? So minimum we can see minus 1, comma 1. Sorry, not minus 1. This is plus 1, plus 1. So this is exact solution by Gauss-Jordan method. After finding the gradient, equating the gradient to 0. Okay. So if you do it, you are able to see that the solution is 1, comma 1. Now, if you use this, actually this is for iteration 5000 iteration, and we are starting from for long random guess. We are doing the random guess x1 and x2. We are taking random guess, and we are writing this. So x1 minus this function. So this is actually del f del x1. That is the first del f del x1. So first partial derivative, and this is the second component of the partial derivative, the gradient. We will write it here, and we want to, the step length here is given 0.001. So if you just evaluate this function, okay, then we can see that the solution is 1.4 and some like and 0, 0. Okay, and optimal value is not actually reached here. So if you give here instead of 5,000, if you leave it 50,000, and if you evaluate again, then you can get the actual solution. Why this much difference? because our initial point that we are starting is so long distance. I mean, it is very, very distant. Exact solution is 1, 1, but we are starting at minus 10, comma 10, minus 10, minus 10. So that is a very worst case actually. Very much bad approximation. But if you start from minus 1 and to 1, and if you just give only 50 iteration, then you can see that we are almost, it is giving some different value. It is not giving exact value. So maybe 500 can reach. This is again not possible. So random guess is given. This is a different code, not a theoretical one. So for 5,000, it is almost reaching to the optimal point, 1 and 0.8. So anyway, so the reason I'm showing this one is Mansium. So I have mentioned that we will try to. Okay, I have mentioned several times that if we have a function like this, okay, so if you drop a ball here, so it will come to a point here. If we have a peak, so it will not be able to go up. So we'll try to look at such situation. If we can find a different code, so then we will try to look at some point. So this is another plot we can do. Yeah. So here we have 50,000 iteration. We're starting at -1, -10, and this is -10 also. I mean, far from the original point. And if we evaluate the selection, then we try to find out the solution. So this will be the surface plot of this function. And you can see that one red curve is actually moving. So this three-dimensional plot you can see here. So this is moving to the minimum point. Since I have given so much of iterations, okay, now it is going slowly. If you try to look some other view, I'm not able to do actually. So this is actually not working. It has, let me pause it. I will give a little less iteration, not 5,000. Let me give you only 5,000. So anyway, this is this. My computer configuration is not that much fast. Is not supporting that much. So that is why it is not able to run this program. So if you have a better system that can actually give you the solution. Let me close it. For one more time, I will try to show. So let us try to find the solution that we have discussed for the other problem also. The same problem that we have discussed. Okay. Let me use here was is 7. If you use this function, then you can see the movement of the minimum point actually. That is, let us see whether now it works or not. You can see here. Since I have given the rate of convergence, actually was actually given I have for 7 seconds. Okay. You can see that it will come to this -1, 1.5 point, and it will reach to the point. Okay, anyway, you try to implement them, then you will realize that how this gradient descent method is actually moving to the solution. So here it is. Finally, you make it of this form. So this is -1, 0, the left of it. So this is -1, 1.5. This is the minimum point you can get. Here it is. The minimum point will be here. You can see this is -1, 1.5. So it is actually still moving. Okay, so this I have given 5,000. Now, if you try to look at this function in a
Should I call, sir?
I think he dropped out of this call. Just give him a couple
Yes,
of
sir.
minutes, he'll join back, I think.
So then should leave now.
Yeah, it's 7:30, it's practically 7:30.
Okay, sir. Sir, you are not audible.
Correct. Okay. So if you have any doubt, you can ask me.